we have understood the difference between spontaneous emission and stimulated emission of radiation. And now here we will try to understand actually how a laser works, and we understand that this laser is basically it stands for light amplification of stimulated emission of radiation. Light amplification, light amplification of by stimulated emission of radiation. Now, if we think about a system which is in equilibrium, suppose at equilibrium we have n1 number of atoms. It is the number of atoms in ground state. We have n1 number of atoms in ground state at thermal equilibrium, and the number of atoms in the excited state is n2. So n2 is the number of atoms in excited state. Okay, so we have a system where we have n1 number of atoms in ground state, say E1, and we have n2 number of atoms in excited state, say E2. Okay, so that should be clear. Now the number of atoms in any given energy state of the substance is known as population. So we call it as population. And the relative population of energy levels as a function of energy in the ground state at equilibrium, we can see that if we show it in terms of an understanding that suppose this is my population and here is my energy. Now I can have a situation like this. The number of atoms in ground state are extremely large, then in some higher state it's lesser, then it goes on decreasing, it goes on decreasing, oh no, it goes on decreasing. And the ratio of the number of atoms in the states, say for example state 1 and state 2 that we have here, that 2 in equilibrium, that ratio can be given as n2 by n1 equals e to the power of minus times E2 minus E1 by kBT. So E2, we understand the number of the energy of the atoms in state N2, and E1 is the energy of the atoms in state N1, and K is the Boltzmann constant, and T is the temperature. And this is what we have here. So so at room temperature, now this equation at room temperature, so on an average, let us think about 300 Kelvin. The number of atoms in higher energy state is very small as compared to the number of atoms in the ground state. Or the number of atoms carrying low energy state. Now, a laser is based on stimulated emission of radiation, and we have talked about stimulated emission. It's a forced emission where you already have to have the atoms in the excited state. So the population of atoms in the higher energy state must be greater than that of the population of atoms in this ground state. So what does it mean if I have to term it in some other words? The population of atoms is to be inverted for stimulation. It is to be inverted. That means N2 has to be greater than N1. And the inversion of the population of atoms has to be carried out. And this inversion is called as, we call this inversion as population inversion. So this thing is population inversion. Now, the process of inverting this population of atoms that we talked about, that phenomenon is known as pumping. We call that phenomenon as pumping. And pumping can be of different types. Like if I take an example of, suppose the most popular way of pumping is known as optical pumping. So what we have is we have we have optical pumping. Now, what we do in optical pumping is the material that we have, it is illuminated with light of frequency nu. And what we have h nu equal to E2 minus E1. The atoms in the ground state, they absorb energies, and they absorb the energy of the incident photon and they jump to some high energy state. They come to the high energy state. Now, if this material is in the form of a gas, say for example, then the population inversion can be obtained by another method known as electrical pumping. Now, population inversion is clear that what we have, we want to have N2 greater than that of N1. Now, whatever the mechanism we are applying, that should lead to this kind of transformation of the atoms. And now, in these cases, I mean, in the case of electrical pumping, if we talk about the population inversion is due to inelastic collision of between the atoms and the electrons in the discharge tube. That you will have electrons hitting the atoms, and you try to achieve that kind of inversion. Now, these methods of pumping do not produce desired population inversion in case of two level energy scheme. And now this is because of the same reasons, the reasons of what the atoms in the higher energy state that we have here, E2, and here we have E1, they jump to the ground state in 10 to the power of minus 8 seconds. So a very short lifetime for the atom to be in an excited state by simply emitting a photon, by simply emitting the radiation. And atoms do not last long to be stimulated. So they have to stay there first for some time. Only then we can stimulate these excited atoms, these electrons in the excited atoms. And what happens in case of two-level system, the problem happens that the moment you try to take them to the excited state, they come back to their ground state very, very fast. So automatically what we have is the spontaneous emission of radiation. So if we have to go for stimulated, if we have to go for stimulated emission of radiation, for stimulated emission of radiation, the atoms that are staying in the higher excited states, they should stay there with longer life. They should stay there with longer life. That's the fundamental requirement of the system. And these energy states are called, the energy states that where they will stay, suppose this is that energy state. These energy states are called as metastable states. Metastable states. And because they are stable on an atomic scale, although they may last for of the order of the time of 10 to the power of minus 3 seconds, or simply I should say 5 milliseconds in this metastable state. So 5 milliseconds is more than that of 10 to the power of minus 8 seconds. So the atoms in this metastable state last long enough to produce the good amounts of stimulated emissions that we can think about. Now, if I would like to have a sketch first, let me take a system like I have an energy, the number of atoms in energy state E1, number of atoms in energy state E2, and no, let me call this E3, it should be on the top, and let me have another E1. Okay, now what we do is Uh, Now, suppose we have a material whose atoms can exist in some three different states, E1, E2, and E3. And the energy states having energy E1, this is my ground state. So this is the ground state. The energy state having E3, this is my excited state of atoms. Okay, and can stay there only for 10 to the power of minus 8 seconds, only for this short time. And the energy state that we have E2 here, this is the metastable state. This is the metastable state, and in which an atom can stay. It can stay for a time of the order of what, 5 milliseconds. Now, let's try to understand the system over here, the working here. Now, let us assume that all the atoms of the material are in this ground state. Okay. Now, suppose some incident photons, each of energy h nu dash. We have some photons of energy h nu dash, such that this energy supplied is E3 minus E1. It falls on the material. Now what will happen? The atoms in the ground state that we have, they will absorb this energy and they will go to the excited state E3. And what is important to be noted here is that the number of atoms that are raised to this excited state E3 are equal to the number of incident photons. That should be the case. Okay. Now, since the lifetime of each atom in this excited state is very small, so all the atoms in the excited state E3, what they do, they jump to the metastable state. What they do, they jump to the metastable state. So what we have given the energy, they have gone directly to the excited state. So what is happening here is that since the lifetime of each atom in this excited state, E3 is very small, and what's going to happen here is that the excited state, the atoms in this excited state E3, they prefer to go to this state in that very short span of time, which is of the order of 10 to the power of minus 8 seconds, by spontaneous emission. And each photon emitted has an energy. Here we will have photons from here, they will have energy h nu double dash. And that will be simply E3 minus E4. Sorry, E3 minus E2. It's coming from this to this. Now, the atoms that we have in this metastable state, what's going to happen? These atoms that we have in the metastable state E2, they can reside for a longer period of time than the excited state of E3. It means the atoms reach a metastable state E2 much faster than that of the atoms leave the energy state E2. Thus, the population of atoms in this metastable state is more than that of the population of atoms in the ground state, because they have a delayed transition. So this situation is known as population inversion. This is what's called as population inversion. And the process of obtaining this population inversion is called as optical pumping. So you are able to do this kind of thing by optical pumping in this particular case that we are talking about as a sort of example. Now the atoms that we have in the metastable state E2, they are bombarded. Now they are bombarded. How should I show it? Okay, now they are bombarded. Once they are in a state of in metastable state. Now they are bombarded with the energies h nu. And this h nu gives us E2 minus E1. The atoms in the metastable state E2, they are stimulated to jump to the ground state by emitting a photon, and the energy of each photon is h nu equals E2 minus E1. These photons, along with the bombarding photons that we are bombarding on the system, have the same energy and they are in the same phase. So what's happened? We get an amplified, there's a state of amplification because we are able to have atoms in a state, in a metastable state, and the number of atoms in the metastable state is very large. And this is done by instigating the population inversion, and in this particular case, the optical pumping. And a coherent beam of photons comes out. So there is a transition from this metastable state to the ground state. And while we have this transition, we have the photons, and the photons are in same phase and they have the same energy as that of the incident photons. So this is how a laser works. This is basically the basic way to understand the mechanism of working of this light amplification of stimulated emission of radiation. Now, these lasers have tremendous applications. These lasers can be used in industry. You can cut down heavy metals, and we can generate holes in diamonds. We have laser surgeries, and we can fix the problems of eyes using lasers. They're used in communication. They're used in space exploration. They are used in making holograms. They are used in military operations. They are used in pollution measurements, and they are used in scientific research. And here I would like to end this talk.